Hello, this is Unit 4, which is Chapter 3, and B because it's kind of in the middle part of the chapter. And it's still on the nature of graphs. So day 1 is about the inverse functions and relations. And functions and relations pretty much mean the same thing for right now. For something to be a function, there are some criteria rather than just a relation, but all functions are relations, not all relations are functions. But don't worry too much about that right now. All we really need to do, so just as an overview, to find the inverse of a function or of a graph is to swap the x part of the coordinate and the y part of the coordinate. So if these points in example 1, if these are the points of something that you could graph, all we would do is swap them. So the inverse then would be the points 5, 1, 10, 7, negative 4, 3, and 5, 2. Easy enough. So whatever we start with, swap them, and that is the inverse. And this is this is just a discrete function, if you will. It's just some points, and so if you wanted to find the inverse, that would be the inverse. When we actually have a function instead of just points, we have to do a little bit more work. We should know something about transformations. So the parent function of this graph would be an x squared, and it's just a parabola that's right at the origin. The vertex is at the origin, but this transformation says it's going up 3. So it helps to have some knowledge of the previous part of the unit, in that this graph is identical. It's just up 3, and then it's going to go something up like this. The reason being that it's helpful to know what the graph's going to look like is because if we make a t-chart of just x and y ordered pairs, we would want to know which x values to use for our original function, just to see which points are what. So we see that the vertex is at 0, 3. And so a good picture of the graph then would be a few points to the left of 0 and to the right of 0. So negative 1, negative 2, 1, 2. Those are the ones we want to use. And you can type this on Desmos if you want to see what it looks like. If we can't remember, this is just x squared plus 3. So you see the vertex there. You can also see, if you check it out right, that it goes through this point 1, 4, and you can see it's a mirror image on the other side. So we could plug these in and just see what they look like. If you did, this will get easier. You don't necessarily have to plug them in and evaluate it for every single problem once we know what we're working with. But if I wanted to know what the ordered pair was when x is negative 2, I'd plug it in. Negative 2 for x squared is 4, plus 3 is 7. Same thing, we could plug in negative 1, and you would get negative 1 squared is 1, plus 3 is 4. So I did the left side here. Negative 2 is 7. 2 is right there, that point. Negative 2, 7. And negative 1, 4. Negative 1, 4. And we know something about parabolas, and there's a mirror image on the other side of the vertex. So this point would be there, and this point would be there. And all that means is that 1, 4, and 2, 7 are also on this graph. So we have a few points. We have about 5 points to have from the original function. And now we know about inverses. All we would need to do is swap the two or parts of the ordered pair. So my new one, inverse, is the new x and the new y are just flipped. 4, negative 1, 3, 0, 4, 1, 7, 2. And we should graph this on the same graph just to see what it kind of looks like. Maybe we'll make a cool design. 7, -2 is down here. 4, -1. 3, 0. 4, 1. And 7, 2. So the inverse looks like this. And you can see it kind of just went sideways. So, and that's kind of brings us up to an inverse, a function and its inverse are symmetric over the line y equals x. Line y equals x just goes up. Its slope is 1, so up 1, over 1, up 1, right 1, or down 1, left 1. And you can see it's just symmetric over that line. You see, like if you folded this paper in half, if this were a paper, folded in half along this line, this would line up right on top of this. So that's what that second bullet point means. But really, in terms of how we do this, we just generate ordered pairs and then swap your x and y's. Ta-da. So this is an absolute value function. We know the parent function is absolute value x. If you're not sure what it looks like, you could put it on Desmos. So you can get the absolute value brackets by hitting Shift and then the button above Enter. Or you can go down here and it'll give you an absolute value x. And you see it's basically a v. Basically, we have a line to the right that's slope is 1, up 1, over 1, and a line to the left that the slope is -1. So up 1, left 1, up 1, left 1. And so this would go, this would be the parent function. I'll erase this in a second. The transformation that happened is left 3, because inside +3 means left 3. So we don't have that. We actually have, from what our actual function is right here, is centered right there. It goes up and to the left. And we could think right now, just to be consistent and complete, I guess, this will be symmetric over the line y equals x. So if I had an imaginary line right here, just to get an idea, if I folded this thing in half, this line is going to appear over here somewhere, and it's going to go up, and this one's going to go down like that. Okay, so that's kind of where we're headed, but we can't be sure. Let's get some ordered pairs. Since I know that this is centered at 3, 0, my XY chart should be 3, 0, and then a couple points to either side of it. So this would be, oh, I'm sorry, this was -3, 0. This would be -4, -5. This would be -2, -1. And we can generate a couple ordered pairs. Let's plug in -5. And when we add these, we get -2. Absolute value, you can throw those brackets away as long as you make this thing positive. So we get 2. You do the same thing, plug in -4 plus 3. This gives you a -1 inside the brackets. Throw away the brackets, make it positive, +1. So we can see that these points should be on the line that I graphed the translation of the parent function. -5, 2, -4, 1. And similarly to the last problem, we have symmetry. This is absolute value graph is always symmetric across its vertex. So we'd have a point here and a point here. We can certainly keep on plugging in points, but it's a little tedious. You would just plug in, -2 plus 3 absolute value, get a 1, throw the brackets away, make it positive, 1. But it's going to be a mirror image across the vertex, so that part's 2. Then we want the inverse. It would just be 2, -5, 1, -4, 0, 3, 1, -2, 2, -1. Now if we plot those points, 2, -5, 1, -4, 0, 3, 1, -2, and 2, -1. You can see it does look just like that. Basically, you can kind of think of reflected over the line created by y equals x, or it's symmetric to that line. All right, here's another example, a couple more examples. So I'll try to go a little bit faster. We see the transformation is up 4. The parent function starts at 0, 1, and it's over here like this, but then we're up 4. Okay. We could, there's not going to be anything to the left. That's going to be an imaginary number. If you plug in -1, you're going to get an imaginary number. Can't graph it on here. So we'll pick a couple points. We started at 0, and we get 4. So square root of 0 plus 4, obviously. We could plug in 1, square root of 1 plus 4. That's good. Square root of 1 is 1. Plus 4 is 5. And then I jumped, the next point I had is I jumped over to 4. Because I wanted to pick points that work in this function. I don't want to plug in 2 here because square root of 2 is going to be an irrational number, big decimal, gross. So I plugged in 4. Square root 4 plus 4 gives me 2 plus 4, which is 6. And we can, the next one we would want to generate would be the next perfect square that you could take a square root of, the next number. And the next perfect square up is 9. Square root 9 plus 4, this is 3 plus 4 is 7. And let's just stop there for now. That means that our inverse, our xy, is 4, 0, 5, 1, 6, 4, 7, 9. 4, 0, 5, 1, 6, 4, and if we kept going, it'd be 7, 9. So you can see it kind of goes up like this. That's the inverse function. Again, just to sum it up, really, the whole point is once you have a list of ordered pairs, you know, your XY table, just swap them. Again, it's important to use this next example. It's important to use your transformation knowledge, just so you're not guessing at which points to put in for X and Y. You know, a lot of times we start off doing -2, -1, 0, 1, and 2, but they may not be the best points. It may only show like half the graph. So let's think about what those should actually be, where the vertex of this graph would be. Okay, parent function's at 0, 0, but we are translated right 3 and up 1. So my actual graph won't be parent function. It would be parent function looks similar, but it is shifted right 3 and up 1. So it looks like we're starting with our vertex. Instead of those just generic points, we'll start with 3, 1, we know is the vertex. And then we'll do a couple points to the left, a couple points to the right. So 2 and 1, 4 and 5. And we should plug it in just so we get at least a couple where we know the symmetry lies. So we have at least one side of it. This would be 1 minus 3 squared plus 1. 1 minus 3 is a -2. Order of operations, we did parentheses, now we're doing exponents. This is 4 plus 1, which is 5. So 1, 5 is right there. Do one more. plug in 2 minus 3 squared plus 1 to -1 squared plus 1, which is anything negative squared is positive. 1 squared, 1 plus 1 is 2. 2, 2. All right, and we have symmetry because, you know, that's the nature of a parabola, is through the vertex symmetry to the left and to the right. Mirror image of your points. So 4 is going to be also right there. 5 is going to be right there. So we can see what those points are. It's we have 2 and 5. And then we want the inverse. So this is what we need. 5, 1, 2, 2, 1, 3, 2, 4, 5, 5. Graph it. 5, 1, 2, 2, 1, 3, 2, 4, and 5, 5, 5, 5. So this is the preferred method because if we were to think of this, that's a bad drawing. If we were to think of this as something that is symmetric over the line y equals x, this graph goes through y equals x. So it's kind of hard to think of it folding it over like this and seeing exactly how it would line up and not. And we have, that looks just crazy. So in black is the inverse function. All right, I hope this video helped. And again, the whole point, just swap your x and y values once you have a list of ordered pairs that are from your function. And then you have a graph of the inverse function. All right, good luck.